Okay, so I think we'll get going. First of all, this is actually going to be my last lecture. We need to leave before the evening. So what I'm going to do is condense some of the material from the last two lectures. Luckily, a lot of the material is kind of, expansionary. So I think I should be able to cover the kind of kernel of what I wanted to say in these last two lectures. But let me kind of start with just a bit of perspective, and maybe I should have started at the beginning of the first lecture with this. But somehow in the course of the lectures, you've seen what you could think of as tricks, or there's some kind of special mathematical properties, things like these Cauchy identities or this RSK correspondence. Or today, you'll see something called the Yang-Baxter equation, solutions to the Yang-Baxter equation. And these seem kind of magical. And then what you can do with them seems also kind of magical. And it's not that these came out of thin air. Actually, the synthesis of a lot of these ideas basically came from people spending years and years looking at physically interesting models. So there were kind of motivations for studying the models. And for instance, the model I'll talk about today is a 6-vertex model. People were interested in studying from the perspective of ice and modeling other types of chemical systems. But and then somebody smart happened upon a nice relation that somehow simplified the analysis, or actually allowed you to make progress. And then people spend a lot of time trying to understand what this miracle was and what caused it, and put it into the most general framework. And that's somehow the perspective that I'm taking, is showing you a cleaned up version of a lot of things that took decades and decades for people to understand. So from one perspective, sitting in the audience, you might say, well, how would you ever have come to these conclusions or these objects? But of course, once you understand some of the structures, it's not that I'm just giving you some magic tricks. It's that I'm giving you an idea of mathematical structures that can give rise to probabilistic information. So for instance, today we'll talk about this Yang-Baxter equation. I'll give you a solution to it, but there are many solutions, more complicated solutions, and each solution can bring with it the analysis of a new type of probabilistic model. Or these Cauchy identities, this idea of having these kind of measures which have these nice forms in terms of products of symmetric polynomials and things of this sort. These are much more general than just for sure polynomials. So once you understand that somehow that structure is useful, you can start to generalize that structure and come up with more and more models. You can also come up with tools to use that structure. And so both of these are very profitable domains. And the same, of course, with RSK. So that's just the sort of preface, suffix, or whatever I want to say, so that you don't approach this as just a bag of magic tricks, but rather certain techniques, certain ideas, core ideas that you can either apply or you can continue to expand upon in some form or another. So the model that we'll be primarily studying today is it's different than we've seen before, but it's not so different. It still depends. So it's going to be the inhomogeneous stochastic 6-vertex model. And in a sense, this is a model that underlies lots of other things. It's not going to be clear, and maybe I'll add something to the lecture notes when they get published. But from this model, you can actually get lots and lots of other models. There's a process which is called fusion, which takes this model and produces more complicated models, but preserves the structure of the model. So for instance, last passage percolation, or this log gamma polymer, both can be derived from limits of the fused stochastic 6-vertex model. So what I'm saying, the point of this is to say that the analysis of this model actually can be generalized through this procedure that I'm not going to actually explain, but to give the analysis of lots of other models. So there is some sort of kernel in the nature of this model. So this model is going to depend, again, on some set of inhomogeneities, A and B, And it's going to assume, as before, that the AI bj's are between 0 and 1. And it's also going to depend on a parameter t, which is also assumed to be in 0, 1. So it depends, and this parameter is just fixed. So the a's and the b's are inhomogeneous. So what is the model? It's the following. So I have a corner, a quadrant, and you should think of this as having some boundary conditions. And of course, you can choose other boundary conditions, but I'll talk about somehow the nicest one, and we'll see why it's nice a little later. So the boundary condition is that you have arrows. So you should imagine that there's a lattice behind here, Z2, and each horizontal point coming in from the y-axis has a horizontal arrow pointing inward. And each point on the x-axis has, well, I'm not going to leave it totally empty, but it has the lack of an arrow. So the boundary condition is all arrows on the left axis and all not arrows on the bottom. Now, okay, what do you do from here on out? Well, what you do is, first of all, let me give you vertex weights. So as the name suggests, there are 6 types of vertices in this model. What do I mean? Well, what's really going to happen is we're going to have some sort of tiling model of vertices of different configurations. And so I give you the configurations, I give you the weights, and I'll tell you how they go in. So you could have a vertex. So I always think of, when I think of vertices, I think of the state of the incoming. So what's to the left and below, I think of these as inputs. And I think of what comes out from the top and to the right as outputs. Okay, so if I have an input which is empty on both sides, then the weight of going and becoming empty is 1. So this model is going to conserve. So all of these vertices are going to be conservative. So they're going to conserve arrows, in the sense that if I have 1 arrow coming in, 1 arrow can come out. 0 arrows in means 0 arrows out, and 2 arrows in means 2 arrows out. So the next kind of trivial case is that I have, arrows coming in from below and to the left, and so they leave. And that happens also with weight 1. And then the sort of non-trivial cases are that I have a horizontal arrow coming in, and it departs horizontally as well. It could come in and then turn. I could have a vertical arrow come in and then depart vertically, or I could have it come in and turn. So it's easy to convince yourself that subject to the conservation of the number of incoming and outgoing arrows, these are the only 6 configurations in which I have at most 1 arrow per edge. There are models whereby you allow multiple arrows per edge, and then of course it becomes more complicated, but we're not going to deal with that. Now the weights are stochastic in the sense that if I fix the input and I sum the weights over the output, I should get 1. That's what the word stochastic means in this context. And so let me write down what the weights are. So in general, they take the form of 1 minus z over 1 minus tz. This is 1 minus that factor, so it's 1 minus, well, I suppose I could write down what it is. I think it's something like z minus tz, right? So if I add these 2 things together, I should get 1, and I think I get 1 if I check it, right? And this one is t times 1 minus z over 1 minus tz, and here I should get, I guess, whatever I need to. So it should be 1 minus t, 1 minus tz. Well, of course, I haven't told you what z is. So if I'm at location xy, then the z that I use, I assign the value of ax times by. So the inhomogeneities come in the form of this z. This z has a name. So z is called the spectral parameter. T is sometimes called the quantum parameter. So it's sometimes denoted by q as well. So the spectral parameter can vary in this doubly inhomogeneous way, but the quantum parameter stays fixed. Now, what do I do with these weights? So first of all, it should be clear that the sum, as I said, the sum of these two weights sums to 1. These two weights sum to 1, and then, of course, each one of these is 1. Okay? So that's the stochasticity. We should assume that the weights are individually positive, and I think the assumptions that I gave imply that. So for instance, if z is between 0 and 1, and if t is in between 0 and 1, I think this, well, okay, you can check. But you need to assume positivity. So now how do we use these weights to define a probability measure? And what is the probability measure on? So what the measure is on extensions of these boundary arrows. So you think of these arrows, and when you know the boundary arrows on the edge of this quadrant, you see on the bottom, maybe I'll move here, on the bottom left corner, you have a situation where you know both inputs. Right? You know that there's an arrow horizontal and nothing coming in vertically. And so now what you do is you look at your chart and you say, okay, so I need to choose one of these two outputs. Either the arrow can continue horizontally or it can move vertically. And I use these weights, I think of these as probabilities, and I flip a biased coin according to these probabilities, where z is assigned a1, b1, because I'm in the 1, 1 position. And so I flip a coin according to that probability, and I get an output. And depending on the output, I choose one of the two types of outgoing arrows. So maybe my arrow continues horizontally, and of course, then nothing comes out vertically. And now you see I have two places where I know the inputs. I know the inputs here, and I know the inputs here. And I can continue recursively sampling from my measure. It doesn't matter the order in which you do it, because it's a local update. This is really the same, in a sense, if you remember the last passage, percolation, we had this recursion relation that said once you know the kind of two parents, you can compute the last passage time at your location subject to some stochastic weight. So, we continue the process. I don't know. I'll imagine that this particle this arrow goes to the right again, then maybe it goes to the right one more time, and then finally it turns up. And so that means that kind of continuing in this direction, you have emptiness. And then up here, maybe this goes to the right, to the right. Each one of these is a decision, but let's say that it happens to go to the right, and now you have a collision. So the collision means that you are forced to kind of bounce off of each other in this way, because that happens with probability 1. So now this particle kind of turns, this arrow turns, and you continue along in your choice of how to proceed. So, okay, maybe this one actually turned up initially, and so that actually forces all of the other ones to go up. It kind of creates this packed configuration. And let me just kind of continue to populate the model a little bit more. So we can kind of go over, this one goes over, up. Okay, so after some amount of recursion, I've sampled a configuration on some region. And again, the probability of this configuration, well, either you could think of it in this Markovian way, or you could just say, well, I look at every single one of these vertices, I take the product of the weights, and that gives me the probability. Now, I want to mention one thing, which is it's possible you've seen the 6-vertex model before. This is a popular model in statistical physics. Usually, in the 6-vertex models, you don't have this stochasticity. So usually, the weights of the 6-vertex model are something like A1, A2, B1, B2, and C1, C2, and they don't sum to 1 in any sort of nice way. If that's the situation, then the model needs to be defined relative to a closed boundary condition. So you have some region in Z2, you specify okay, maybe it's not a circle. Maybe you have like some sort of domain wall boundary condition. You specify certain boundary conditions on all of the 4 edges. Maybe you have arrows coming out in certain locations. And then you say, subject to these boundary conditions on the whole region, the measure that I look at is given by taking the product, so the probability of seeing a particular configuration of arrows in between is equal to the product over all the vertices in between normalized by a partition function. A partition function which is the sum over all potential configurations, and that can be very complicated. You see, because here we have stochastic weights, first of all, we don't need to enforce any boundary conditions in this sort of infinity direction, and second of all, we can sample this Markovian. So we don't need to do any normalization by a partition function because in a sense the partition function is 1. Everything sums to 1. So it's very nice in that sense, and so you can really think of this as some Markov process. And you'll see in the notes, and I won't go into this in detail, but this is a Markov process that has, even without doing any sort of special fusion stuff that I'm not going to tell you about, this is a process that has many nice limits in its own right. For instance, there is a scaling limit of this process that brings you to the asymmetric simple exclusion process. If you scale your parameters and correctly, you'll get to this, this classical interacting particle system where particles jump left and right with some rate, I don't know, L and R, subject to not being able to jump on top of each other. Okay, so it's not immediately obvious, but basically you think of these as the trajectories in some temporal direction, which is going to be ultimately diagonal of these particles, and then you do a scaling in which the particles somehow move in this Poissonian continuous time manner. So you can find various discussions of limits and things of that sort coming up in the notes. Any questions about the definition of the model? Let me define one more thing about the model, which is something called the height function. It's not a complicated definition. You define the height function of the model to be equal to the number of arrows, the number of these level lines. You think of these arrows as level lines. So you think of 0 as the height on the bottom here. And then each time you cross one of these level lines, you increment your height by 1. So the height in this region is 1, in this region is 1. In this region it's 2. In this region it's 3. It doesn't change when you cross. Maybe I'll erase these dotted lines for the moment. In this region, 4, region 5. So of course the boundary condition has the fact that the height function on this boundary increases linearly, and the height function here is just 0. And so somehow what you're looking at is some transition from flat to linearly increasing height. And this creates for you some random surface. And again, natural questions are to understand the scaling limit of the nature of this random surface. So for instance, just for concreteness, you might ask the question, if you go off in the 1, 1 direction, you go off to some very high point, what's the height function? And how does that depend on the slope? Is there some sort of law of large numbers that if you go off at slope theta, you have a certain height, asymptotic in distance n? Are there fluctuations around that? What's the nature of the fluctuations? How correlated are they as you change your direction, both in the radial and the transversal direction? Okay, so all of these are very interesting questions. They end up being very related to the questions that we had asked about last passage percolation, because these models end up being in the same universality class. Okay, so this is the stochastic six-vertex model, and what I want to give you now is the arguably most important property of this model, which is that it satisfies the Yang-Baxter equation. Okay, so I've kind of mentioned those words before. Let me first do something. So here are the vertices. Let me just, I'm going to also consider a version of these vertices that are rotated by by 45 degrees. So let me just draw them. So imagine rotating this by 45 degrees. So I have a cross here. This one becomes, I guess by negative 45 degrees, right? This becomes like that. This one becomes like this. And this one becomes, okay, so I've literally just rotated these by 45 degrees. And now the inputs you should think of as being here, and the outputs here. Okay, so why have I done this? Well, I've done this because I want to give a relation between the model and certain partition functions that involve these rotated vertices. Now, let me kind of say something historic. I'm not going to give the details of this, but historically, the Yang-Baxter relation is really a relation involving 6-vertex weights. So it's going to say something like, if you have weights of the 6-vertex model and you specify boundary conditions at all of the kind of external points of this picture, and you sum over all potential configurations of arrows that will achieve these boundary conditions, that this weight will be the same as if you had kind of taken your cross and pulled it through. Okay, so right now I'm just drawing pictures, but I'll explain precisely what I mean. So Yang-Baxter is usually written pictorially as in this form. It's what looks like a braid relation. You can take a cross and pull it through. Now I need to tell you what the heck this means, but the general notion of the Yang-Baxter equation is that you have some state space for what sits in these circles. So for instance, the most basic version of the Yang-Baxter equation says each of these circles can be inhabited with a 0 or a 1. I think of zeros as there being no arrows coming out, and a 1 as there being one arrow coming out. So right now I've kind of, okay, maybe I shouldn't, I've drawn solid lines, but these are not, I don't mean arrows. I just mean these are paths. So, okay, so I have arrows. So maybe I have 0 arrows coming in, 0 arrows going out, and 0 arrows going out here. And of course, then I'm forced that I have 0 arrows at every internal place. Okay? So the partition function here would just be 1 because I have no choice and all of the weights will be 1. And here similarly it would be 1 as well. So the Yang-Baxter is looking for vertex model weights which satisfy this sort of commutation relation, this intertwining relation. And the initial solutions really involved using these 6 vertex weights for all 3 of these different locations. So you would have potentially 0s and 1s on every boundary point, and then you would look over all choices of how those 0s and 1s or those holes and arrows could propagate through the model and satisfy the boundary conditions. You'd sum over the weights, these 6 vertex model weights, and remarkably you'd see that if the weights satisfied certain relations, in particular these weights work, that you have this satisfied for all boundary weights. So that was the sort of 1970s realization of Baxter and Yang, and that's why their names are associated to it. And then you can kind of expand around this and say, well, can I find more general solutions where I don't restrict myself to having just 0s and 1s, 0 particles or 1 arrow? Maybe I can have more. And so what I'm going to give you is a solution in which I still have these horizontal spaces are restricted to 0 and 1 arrows, but the vertical spaces are what are called higher spin or bosonic states, and they can allow for an infinite number or an unbounded number of arrows. So this might sound weird, but let me describe it. Okay. So I need to define one other set of vertices. And as I just indicated, I'm going to allow, so I really have somehow 3 different types of vector spaces. I have a vector space that's corresponding to this line that can have generator, which has basis elements, which is basically 0 and 1. I have a vector space on this line, which is 0 and 1. And then I have an infinite dimensional space corresponding to this line. And so the vertices, so these of course, this is the stochastic 6-vertex model. So I'm going to describe something that's called the T-boson model, which is just a collection of weights associated to certain types of vertices where you allow infinitely many or unbounded number of arrows in the vertical direction and 0 and 1 arrows in the horizontal. So this will depend on some parameter. It'll also depend on some parameter u, so t and u. And there are 4 fundamental types of vertices. There are vertices in which, so I'm going to draw this as kind of a solid pipe almost. So if I have no arrows coming in horizontally and no arrows coming out horizontally, I could imagine that my pipe has inside of it m arrows and they just go straight out. So it's still a conservative system. And there are really 4 types of horizontal states. I can have no arrows coming in and 1 arrow coming out horizontally, in which case if I have m plus 1 arrows coming in vertically, one of them gets pulled out and I have m arrows coming out on the top. I could have a situation where I have 1 arrow coming in and 1 arrow coming out, and then the m arrows that come in from the below also come out. You can kind of think of this one getting pulled up and this one getting pulled over. And then finally, I can have 1 arrow coming in and no arrows coming out, in which case I end up with m plus 1 arrows on the top. Okay, so these are the types of vertices. You see there's an unbounded number of these because I can think of m as arbitrarily bigger than or equal to 0. Okay, so I need to have at least 0 arrows. I can't have negative numbers of arrows. So these are the types of vertices, and then the weights are very simple. The weight of this one is 1. This is u. This is u. This is 1 minus t to the m plus 1. Okay. Seems a little complicated, but let me tell you what do I do with these weights. And okay, maybe I should also tell you that these T-boson weights come actually from these stochastic 6-vertex weights through this process of fusion and then through some specialization. So really the relation I'm going to give you right now, you can derive from the fundamental relation that is this Yang-Baxter equation for the stochastic 6-vertex model. You can kind of lift that into the following relation. So here's the theorem. I'll state it pictorially and then just tell you what it means. So the statement would be something like, for all I1, J1, I2, and J2 in the set 0, 1, and all I3, J3 that are non-negative integers, we have the following equality, and it's really an equality as functions of t, u, and v. So we have the following picture. So I'll draw the picture, which will look a lot like that picture, but then I'll tell you what the picture means. So we're going to take a little bit of time to digest. You know, maybe you've seen the people draw these Yang-Baxter equation relations before, but never really understood what they meant. You know, are they just some pretty pictures? So let me describe what it means. So first of all, I think of there as being I1, I2, and I3 arrows incoming at each of these inputs. So you think of these as the sort of inputs. And I think of there as being J1, J2, and J3 arrows coming out. And similarly, on the left, I have the same boundary conditions, I1, I2, I3, J1, J2, and J3. I need to tell you what vertex weights to use. And so the vertex weights that I use here are exactly these 6 vertex weights where I've specialized my variable z to be equal to u over v. So I'm just going to draw that with an arrow labeling this value of the spectral parameter. And here I use the spectral parameter u, and here I use the spectral parameter v. And let me see, is this the version I want to use? Actually, let me not use u and v. Sorry, let me write this differently. Let me not use u and v. Okay, so I'm going to use a times b, which is anyway the thing that we're always taking our z to be a times b. So I have 2 parameters a and b, and then I have parameter a here and parameter b inverse here. So what does this mean, this picture? Right, let me tell you what the picture means. Pictures, as before, pictures mean partition functions. So I specify the outgoing arrows. Let's say I specify all of the I1 and I2 equals and I3. Let's say they all equal 0, just the most basic example. And then, well, okay, I could choose arbitrary things for J1 and J2 and J3, but unless they're equal to 0, the partition function is 0. Because if I have 0 incoming arrows, and I have a conservative system that conserves the number of arrows in this sort of direction, then what comes out needs to be 0. So I get basically partition function 1 if everything is 0 and otherwise 0. What if instead I had, I don't know, 0 arrows coming in here and 1 arrow here and 0 arrows here? Okay, so then I would be forced that my j's also add up to 1. Now there are lots of choices. So let's say that it happens that I have, I don't know, J3 equals 1. So I could have really 1 arrow coming in, nothing coming in here, and then nothing comes in from below, and I have 1 thing coming out, and nothing goes out. So I need to kind of fill in the rest of the picture. So this arrow could kind of cross through and then get rooted up, or it could have got rooted down and then pushed up through this pipe. Right? So you think of this almost as a game. The particle can either take this trajectory or it can take this trajectory. And for each of those 2 choices, you compute the weight. So you compute the weight first on the left by using, well, whichever of the relevant weights there are. So in the first case, you would use this straight weight, and the other ones you'd use the curve weight. And then inside of these pipes, you use whatever weight you have here. And so the statement is that, and then, okay, we use the weights where we have specialized this parameter u to be a on the top and b inverse on the bottom, and the z to be a times b. And so the statement is then that for any choice, so there's an infinite choice of boundary conditions, for all of these choices of boundary conditions, what I get coming out of both sides, these partition functions, match. And so this, when you pull this cross through, you almost think of these as strings. So you pull it, this thing flips over, and now the a is on the bottom and the b inverse is on the top, and you still have a times b. So you see in the very special case of this, just the 6 vertex model for all of the vertices, there you had fewer choices, right? You had 2 choices here, 2 choices here, 2 choices here, and then the same, so it's an equality of, I don't know, 2 times 2 times 2 times 2. You need to check a bunch of equations. Here, similarly, you need to check a bunch of equations, but in fact, you can show that it amounts to, it suffices to check really 16 equations. So you can choose I1 and I2 and J1 and J2, and then given those numbers, you're very restricted in what I1 and the relation between I3 and J3. And so somehow there are really only 16 equations to check this inequality, because you think of this as an equation in the value of m. Okay, so this is the Yang-Baxter equation. Are there questions about what it means? obviously there can be questions about how the hell you came upon this. Yep.
So what, I mean, there is an M in this definition of the T boson. Where does it appear?
So the M is, so again, this is a statement that it's true for all I1, I2, J1, J2, and I3 and J3 that are strictly big, that are bigger than or equal to 0. So when I specify I3 maybe to be 17, the vertex here needs to use the vertices here where the bottom thing was 17. Now, of course, most of the time it doesn't matter except if you have this type of vertex, something coming in and not going out. And then you get this 1 minus t to the, I guess, 18. Okay. A good question. Other questions? There's a big branch of mathematics that's built around finding solutions to this equation. And this is the area of what's called quantum groups. Okay, so for the last 20 years or 30 years since the 1980s, this has been an area of interest. How do you find solutions to Yang-Baxter? And of course, you can find solutions where you have much more general types of inputs. So rather than just having zeros and ones or 0 through natural numbers, you could imagine having inputs which are indexed by more complicated objects themselves and still try to find equalities. You have weights that depend on more complicated objects than just numbers. And so that's one direction. For instance, you could imagine situations where you don't just have arrows of one color, but you have arrows of arbitrary colors, in which case these inputs become themselves what you call compositions. You keep track of the number of particles of each different type and the number of arrows of each different type. And then this ends up being related. So in the case that I've described here, this relates to the quantum group UQSL2, so rank 2. And if you go to higher rank settings, you end up with colored models. And these colored models have probabilistic meaning. They actually correspond to studying multi-species models like the multi-species ASEP. Second-class particles, third-class particles, things of this sort. So there's a lot of algebra, and there's a lot of related probability. Okay. Again, any questions about this relation? Because we're somehow going to use this relation. I'm not going to prove it. That's something that you can do. Yeah?
To check to understand it. So if I3 and J3 have difference larger than 2, then
you're screwed. It's 0. Both sides are 0. So in fact, for almost all choices of boundary conditions, both sides are 0. And for any non-zero choice of boundary conditions, you have usually maybe at most 2 different terms on each side. So it's kind of, when you actually start checking these things, it's a bit of a miracle, but on the other hand, it's just like you check that the sum of 2 different things is equal to the sum of 2 different things. So it's not hard to check. Okay, so this is the Yang-Baxter. And now that I've written it, I want to maybe slightly rewrite it. So actually, I'm going to erase this. I'll rewrite it in a moment. But I want to introduce maybe I'll give myself a little more room. So the T-boson model actually will come in 2 different flavors. So you see, I have these A vertices and then I have these B inverse vertices. And it'll just be helpful for me to actually call these something different. So when I plug in B inverse for you, what I actually want to do is I want to then normalize these so that this vertex has weight 1. So if I put in a B inverse here, if I multiplied all of the vertex weights by B, I could maneuver myself to have this one having B1. So I'm going to what I'm going to do is the following. I hope you'll forgive me. So I have 2 types of these pipes. I have the pipes that are somehow empty pipes, and then I have what I'll call shaded pipes. And again, it's the same sort of situation. I have M in, M out, 0 in, 0 out, 1 arrow out, so M plus 1, M 0. Okay, I'm just redrawing the same thing, but now I'm shading them so they look like candy canes. And I'm substituting in u is equal to b inverse, and then I'm multiplying all the weights by b. So here I get b, here I get 1 over b times b, so I get 1. Here I get 1 over b times b, so I get 1. And here I get b times 1 minus t to the m plus 1. Now the point of doing this, so first of all, observation is that the Yang-Baxter relation doesn't care if I multiply all of these vertex weights by b, right? Because all that it does is it multiplies the partition function on the left and right by b. So that nothing changes. The reason why we're doing this, so these are the sort of original vertices, and these, I don't know, I'll call the tilted, or maybe I'll call these the tilted weights. The reason I'm doing this is that I want this weight to be equal to 1. And I want this weight to be equal to 1. And the reason I'm going to do that is because I'm actually going to compose these Yang-Baxter equation multiple times, and I'm going to take a limit of this as the width goes to infinity. And it will be very important that I've kind of turned the weights into things that are normalized at infinity in the right way. So you'll give me a moment and accept that it just will make sense in just a little while to do this. But if I do this, then the Yang-Baxter relation I can write now just in terms of these. It's the same thing, and I've just inserted in these shaded vertices. Okay? And now I'm specializing. Now I'm using A here and B here, so I don't need to put a B inverse. So this is the version of Yang-Baxter that I'm actually going to use, is what's written down here. Okay? So I hope I haven't confused you in this. I literally just did a change of variables. Okay, so now we'll see why I did that. Let me give you kind of the outline of where we're going, because here I started with the stochastic 6-vertex model, and now I'm talking about these T bosons, and so what's the point? Why do this? So what I'm going to do, so my ultimate goal is to give you a relationship. Think of this as something like LPP. And I'm going to give you a relationship between this model, stochastic 6-vertex, and something like the Schur process. Except it's going to be a little bit more complicated. This is a model that has an additional parameter. And it's going to relate to something that's called the Hall-Littlewood process. And the T bosons are going to be used to build the Hall-Littlewood process. You're actually going to define what are called skew Hall-Littlewood polynomials, which when t equals 0, reduce to Schur polynomials. So somehow the picture is going to reduce at t equals 0 to the Schur process. But we're going to give a relation between this stochastic 6-vertex model and this Hall-Littlewood process. And then hopefully, if I have time, the punchline, well, one punchline is that Hall-Littlewood process, by virtue of being defined in terms of these T bosons, enjoys itself a very nice and simple version of a Gibbs property. So it is itself a Gibbsian line ensemble, and it's because it's built out of these T bosons. There's much more that can be said. For instance, the Hall-Littlewood process, you can analyze asymptotics of it. You can't do it in quite the same way as the Schur process. The Schur process was determinantal. We had these nice determinantal formulas. We can do asymptotics in that way. It turns out Hall-Littlewood processes are a little harder to analyze. They're not determinantal. And that would be the subject of a class in its own right. But so I'll get you to kind of the point of this non-trivial relationship, hopefully to the point of understanding that it implies a Gibbs property, and then I'll stop there. Oh, maybe I shouldn't have erased these. I'll leave these in. Okay, so the Yang-Baxter equation can be iterated in the following way. So imagine now that I had, and I'll change from the J's to some other letters. Imagine that I had boundary conditions that I had I1, I2, and then I fix some L, and I have I have these pipes, and I have NL, and then ML minus 1, NL minus 1, so on and so forth until M1, N1. Okay. And each of these is labeled by the spectral parameter. I'll write it inside now. The spectral parameters A and B. And this is, of course, as before, A times B. And then I have some outgoings, J1 and J2. OK, so again, what does this picture mean? This picture means that I specify boundary conditions, I1, I2, that's the number of arrows coming in on the side. J1, J2, that's the number of outgoing arrows on the side. And then M1 through ML is the number of arrows coming in vertically. These can be, of course, non-negative integers. And N1 and N2 are the outgoing arrows. And now I ask, what's the partition function for this picture? In other words, how do my arrows, I look at all ways the arrows could be routed through this picture. I look at the sum over that of the weight of each picture. Now you see, you can apply the Yang-Baxter equation L times. You think of it almost as a zipper. So you take these two sides, you pull it, the cross moves through by Yang-Baxter. The weight doesn't change. So now you, after one step, you end up with a picture where you have this sort of you have, and the cross has flipped the shaded thing up on top. And you continue to pull it until all of these things flip. And Yang-Baxter tells you that each time you do that, the partition function, so you still have kind of fixed the values of all of these outgoing numbers. Each time you do that, the partition function stays the same. And so what you get is that this is equal to the same picture where I've just moved the cross through and I flipped the A's and the B's around. Okay, so for the purpose of drawing this, rather than trying to draw each individual bit, what I'm going to do is I'm going to kind of think of these vertical pipes as like a little package. And so what I really have is I have a bunch of these pipes, but I'm just going to draw it as one big pipe, and I have ML through M1 as the bottom, and N1 through NL. Okay, it's just, you see it's a lot easier for me to draw it like this, but you should imagine that there's really all of these pipes and everything is being routed together. It's just you have a really good plumber who's kind of hidden everything behind some big box. And so the Yang-Baxter relation implies then, so let's see, that this is equal to I1, I2. I flip these around. I still have my M vector. Let me just write it as the vector M, N vector. So I'm writing this as M and N, and then J1 and J2. Okay, so this is implied by Yang-Baxter, but applying it L times. Okay. Any questions about that? I want to make sure that the notation is clear. So I think of really the vector M as the vector N, M1 through ML, and I label them from the right to the left. And I think of these as the number of arrows. So if M was equal to, 1, 0, 0, 1, that would mean I would have one arrow coming in, or maybe I put a 2 here. One arrow coming in here, no arrows, and then 2 arrows coming in at the 4th position. Yep. What was that? Ah, yes, sorry. Yeah. Okay, and this is again AB. Okay, so this is the Yang-Baxter equation iterated L times. So now comes in my choice of normalization. So the reason why this was a nice normalization is that now I can imagine taking L to infinity. So when I take L to infinity, the notion of taking L to infinity is really the following. So I fix a vector of incoming arrows, and I think of it as kind of eventually having no arrows coming in from below. So I fix some some ML, some MVec, which you can think of as in z bigger than or equal to 1 to the, to the natural numbers, and but with the property that eventually it is 0. And same for the n. And so I have my favorite incoming and outgoing arrows, and now I look at a wider and a wider situation. So I look at an even wider picture. I still have kind of stabilized my number of arrows coming in, so I eventually have no arrows. And I have my arrows going out here. And then I have my cross. And this is equal to the, again, the picture with the cross. And the question is, what happens as L goes to infinity? What happens to the Yang-Baxter equation as L goes to infinity? And so the first thing that you'll realize is that if you look at the original type of T-boson vertices, I've assumed that U is strictly less than 1, and I've assumed that T is between 0 and 1. So all 3 of these types of vertices are strictly less than 1. This is the only vertex that's equal to 1. So if ever I were to have a situation where either of these 3 vertices occurred infinitely often, as L goes to infinity, my weight would go to 0. The weight of the picture would go to 0. So the only situation that's kind of stable at infinity is that I have on the top, that I have kind of an infinite collection of these types of vertices. Basically, where horizontally there's nothing coming in. So as L goes to infinity, I'm kind of forced to have an infinite sequence of nothingness horizontally. Because otherwise my picture will get some factor to the infinity, and that factor will be less than 1. And similarly on the bottom, the normalization was such that the only factor that's really stable on the bottom is this one. Of course, this is also equal to 1, but you see, in order to have this factor, I must have had one of the other factors right in front of it, and that would contribute, again, something that's strictly less than 1. So the only stable thing at infinity is having just these horizontal lines. So when I take myself to infinity, I'm forced to have these sort of infinite collections of particle and infinite collection of holes. And so if I take, say, the Yang-Baxter equation where I specified let me imagine the Yang-Baxter equation where I've specified that I have an arrow coming in and no arrows coming in there. You see, I'm forced that this 0 passes through, and I'm forced that the 1 passes through. So whereas usually in the Yang-Baxter relation, you have this property that you can sum over the 2 potential ways that the 0 and the 1 can flip, here, by virtue of taking L to infinity, so this is in the L to infinity limit, you're forced actually to just have a deterministic weight for this vertex, that this vertex is the vertex where the 1 crosses horizontally. And so what you end up with is the following picture. So the limit of Yang-Baxter where I've taken a 1 and a 0 gives me the following. So let me try to write this down. Let me write it clearly. So in this L goes to infinity limit, what I get is that the Yang-Baxter equation becomes equivalent to the statement that, well, this is actually a deterministic cross. This has actually weight 1 minus AB over 1 minus TAB. So rather than, so the partition function will actually factorize, and you get out this factor, because this is the weight of this cross in this L goes to infinity limit. And then you have this sort of infinite, I'll still draw it as a finite picture, but infinite vertex where I have my m's and my n's. And again, I should think of there as being this sort of infinite stream of arrows coming in. And eventually they interact with the arrows that came in from below and to the right, and from above. And then I have my outgoing, J1 and J2. And that this is equal to, again, this picture And here, of course, this is still random. You could have, whatever comes out, you could have different options for this vertex. So this right-hand side is somehow a sum, because you have different options for these internal vertices. This is actually deterministic. Well, not deterministic. There's no summation that you actually need to compute. Once you know what the m's and the j's and the n's are, this is actually just a product of vertices. There's no summation here, because you have kind of no freedom. Okay, so what do I want to do in the remaining portion of time? So maybe I want to do two things. So the first thing I want to do is I want to tell you that what I've written here will give us a proof of the skew Cauchy identity for Hall-Littlewood polynomials. So the Hall-Littlewood skew Cauchy identity. And if I take t equals 0, it actually gives us a proof of the skew Cauchy identity for Schur polynomials. So if you didn't do that exercise, I'm going to do it in a way that you may not have come up with on your own in just a moment. This also allows us to prove that the Schur polynomials, or these Hall-Littlewood polynomials, are in fact symmetric. Right? So again, I made a claim that they're symmetric. If you believed this bi-alternate formula, then it was obvious, but I'll give a proof that the S lambdas and then the Hall-Littlewood generalizations are symmetric. And finally, I'll give a connection between, I'll define something called the Hall-Littlewood process, and I'll connect it to the stochastic six-vertex model height function. In fact, in a very similar way, that a marginal curve of this Hall-Littlewood process is equal in law to the height function of the stochastic six-vertex on a downright path. Okay, so we'll see how much of this I get to, but hopefully some of it. Okay, let's see. So maybe I will erase the middle now. And so the first thing I want to tell you is what are Hall-Littlewood polynomials? What are these skew Hall-Littlewood polynomials that somehow are generalizations of Schur polynomials? And then what do they have to do with these pictures? Well, in fact, they'll be defined through pictures. So first thing to note is, if you think of these incoming arrows, these m vectors, m1, m2, m3, m4, think of these, you can actually associate to each m a partition lambda in a very simple way. So if I have a partition lambda, I can map it into a vector m by simply saying that mi is equal to the number of times that I comes up in, so the number of i's such that, or maybe I should say the number of j such that lambda j is equal to I. Okay, so this is the multiplicity of I inside of the partition lambda. So if lambda was, 4211, or 4221, let's say, then, so 4221, then the m that this would correspond to is, well, it would have 1 time, 2 times, 3 0 times, and 4 1 time, and then it'd be 0 after this. Okay? Is that clear? You're keeping track of multiplicities. Sometimes this is written that lambda is equal to 1 to the m1, 2 to the m2, 3 to the m3, where you just think of these as kind of giving you the number of times that this comes up in the partition. Okay? Sometimes that's a more elegant notation. Okay. And of course, remember that the length of lambda is the number of non-zero parts, and so that's going to be equal to the sum of the mi's. Okay. So I'm going to think of associating my m to a lambda and my mu to a mu to an n. Maybe I should have done mu and nu, but whatever. And I'm going to define these skew Hall-Littlewood polynomials through pictures. So skew Hall-Littlewood polynomials are going to depend, I'm going to give one variable version, so they'll depend on a parameter. So there are actually two types. There's p lambda a, and it depends also on a parameter t, and then there's q lambda, and I'll write b, and also depending on a parameter t. If t is equal to 0, then actually both of these will be equal to s lambda, well, okay, s lambda of a or b. This will be s lambda of a, and this will be s lambda of b. Okay, so this we'll see in just a moment. And how are they defined? So they're basically defined in terms of these infinite volume limits, these infinite L limits of these horizontal vertices. Okay, so p lambda, so I'm defining actually the skew polynomials of A. In the case, so in order for this to be interlacing, so I still require interlacement. So in order for lambda and mu to interlace, the length of lambda can be either equal to the length of mu or at most one bigger. And so in each of these different situations, you have a slightly different definition. So if the lengths are equal versus if the lengths differ by 1. So if the lengths are equal, then this is equal to the partition function in the L goes to infinity limit corresponding to having a partition lambda and mu. So again, I associate the lambda to an m vector and a mu to an n vector with 0 arrows coming in and 0 arrows coming out and spectral parameter A. What do I mean again? So you think of the lambda is telling you where the arrows come in below, and the mu is where the arrows come out from above. You think of there as being this sort of infinite stream of nothing, but eventually they come in contact with these arrows, and then there's no choice. It's going to just be a product of weights of these types. So it's just a product. So this thing is simply a product of a bunch of weights, depending on what the incoming and outgoing thing was. And in this case, it's similar. Again, you need that you have 0 coming in from infinity, because otherwise you get killed by in this L goes to infinity limit. And the only thing that differs is that you allow a particle to come out horizontally. So here, the reason why the length of lambda is smaller than the length of, length of lambda is, oh, maybe I wrote it the wrong way. So the conservation law tells me that the sum of all of the m's and 0 needs to equal the sum of all of the n's and 1. And so that's, of course, why I have this relation on the lengths. And the interlacing really follows immediately from the fact that I have kind of these arrows coming through and satisfying these vertices. So this is the definition. Now I leave it as an exercise to check that if I set t equals 0, I actually get back to the skew-Schur polynomial. So if I set t equals 0 here, I just get a weight 1. I don't have any of these t factors. And you basically see that every time that I have a horizontal line, I get a factor of u, or a factor of a. And so every horizontal line corresponds to a change in the value of one of the parts of lambda. And the total number of changes is exactly the size of lambda over mu. And so I get the indicator function for interlacement times a to the size of lambda over mu. And that's the Schur polynomial, the skew-Schur polynomial. And the exact same thing works in this setup. So this generalizes these skew-Schur polynomials. And now the other thing is I define these other, you see I had this 0 at infinity. I could also have considered the situation where I have a 1 at infinity, and I use my dual T-boson model. And if I do that, I can define this, what I call the Q polynomial. I just need I need something to keep track of both types of these vertices. So then I go from mu to lambda, and I get q lambda over mu. The exact definition, the important, it doesn't matter that much, but the point is that you have these polynomials defined in terms of these vertices. So again, there's some relation on the lengths, and depending on the case, you use one or the other type of boundary condition on the right. So here you have an arrow coming in. You always need an arrow coming in at infinity. And then the question is whether an arrow goes out at 0. OK, and in all cases, if you're not of this form, if you don't satisfy either of these conditions, you set the p and the q equal to 0. OK, so it's easy to check that this second definition also degenerates to Schur polynomials by the same token, by the same reasoning, that this term disappears, and then you just measure the number of terms of a certain type, and there's some sort of complementation process in the Q case you need to deal with. So if I rewrite this relation, you see this relation is saying I take this factor 1 minus ab over 1 minus tab, and I multiply it by something. Well, the something that I multiply by, there's really somehow a missing factor. So I can think of, let me replace this m, let me put a partition mu in here, and then I'm going to put a partition nu up here. Okay, so I haven't done anything, I'm just kind of using some change of variables. And what this identity is saying is that if I sum over the internal configurations, right, the thing that I'm missing, how the bottom pipes are connected to the top pipes, if I sum over this lambda inside, that I have an equality. Okay, that's what the Yang-Baxter was saying. It was an equality of the two partition functions, and the only thing that I kind of have not fixed is how the arrows transition between the two sets of pipes. And so if I write this picture mathematically in terms of the things I just defined, I get the following. I'm going to erase what's up here. So this picture, this Yang-Baxter equation, is equivalent now to the following thing. So this is the weight of the cross. It sounds almost religious. And I sum over my intermediate partition lambda. So this is just a partition. And then you see, well, what do I have? The shaded things are the Q polynomials. The non-shaded things are the P polynomials. Obviously, some terms will be 0 if I have the wrong choice of lambda, but it doesn't matter. So I write lambda over mu in the B variable, lambda over nu in the A variable. And on the right-hand side, I have the same picture, except now I flipped myself around, so I have the P polynomial on the bottom and the Q polynomial on the top, and then I have this summation. So this is equivalent to, maybe I call this kappa, not lambda. Okay. Let me see. I just want to make sure something. Okay. So this Yang-Baxter equation ends up being exactly rewritten in terms of the P's and the Q's as this. And this is the statement, this is what's called the skew the skew Cauchy identity for Hall-Littlewood polynomials. And if you take the special case of t equals 0, this proves the skew Cauchy identity for Schur polynomials that we had interacted with before. So already you see there's some hope. You could start playing these games of constructing dynamics. So first of all, you could play the game of trying to construct Hall-Littlewood processes in terms of these P's and these Q's, and you could play the game of trying to relate these Hall-Littlewood processes to certain probabilistic models by using this skew Cauchy identity and using kind of the factorization of the P's and the Q's. And you can play all of this game. We're not going to quite do that. We'll do something similar to it, though. OK. Any questions before I? Yeah.
So in the Lambda equation also send over the small k. So in the left-hand side they vanish because
Yes.
of this, and do they vanish also on the right-hand side for the same reason?
Here. No, they don't vanish. So, however, once you know what kappa is, it determines exactly what the outgoing arrows are. And okay, another way of saying this is if I fix my value of lambda here, that will fix for me what the values of J1 and J2 are. So okay. Yeah. I should have made this point clear. This Cauchy identity is actually, the Yang-Baxter is a refinement of the skew Cauchy identity. In particular, I take this skew Cauchy identity and I sum over J1 and J2 as well. When I sum over J1 and J2, in this case, I get a factor of 1. So that's why you don't end up with anything here. When I sum over it here, well, what it means is it really allows me to sum over all partitions lambda. Because for a given lambda that interlaces with mu and with nu, I either get a 0 or a 1 coming out. And by summing over all j's, it allows all of those potential 0s and 1s. Here, by summing over all kappas, I can get whatever I will get here, but then I sum over the j's and I get 1. So this is actually, I shouldn't say it's equivalent. This implies the skew quotient. Yeah, thank you. OK, other question. That's a great question. So here's what I want to do now, kind of getting to the end. I first want to use this identity again, use Yang-Baxter so I've proved this identity. I want to prove that first I want to define multivariate Hall-Littlewood or skew Hall-Littlewood polynomials, which of course are generalizations of multivariate Schur polynomials. And then I want to prove that they are themselves symmetric polynomials. We didn't prove that last time. And then I want to give you just a sense as to how to relate these polynomials or measures defined in terms of them to the stochastic six-vertex model, and then I'll end. OK. So let me define. OK. So at this point, I don't think I actually need these weights anymore. The only thing that really matters is that I have these relations. So how did we define multivariate skew or non-skew Schur polynomials? Well, we took a sum over interlacing partitions of products of them, right? So let me define, and of course you can do the same thing for Q in the exact same manner, but let's say A1 through AM. This is defined as the sum over all, it's the same thing before, so all sequences of interlacing partitions that starts with mu and ends with lambda of the product of the p lambda I over lambda I minus 1 in variable ai. Okay, this is the exact same definition. I've just put p instead of s. But we have a picture for this, right? Now we're playing in the world of pictures. So what's the picture for the p is the following. So pictorially, this is equal to, I think of now taking these plumber fixtures, which is made of an infinite number of these pipes, and actually laying them on top of each other. So I'm going to lay m of these fixtures on top of each other, so there's m of these. I have incoming arrow 0 on all of them. I have spectral parameters a1 on the top down to am on the bottom. And I fix that my bottom partition is lambda n, so I fix the boundary condition on the bottom and boundary condition on the top. And then I sum over all, if I'm summing over something, I don't write it. Okay? So I sum over all possible outputs on the right and all possible things in between. And so in fact, that's equivalent to just summing over all things in between, because once I know the things in between, I know what comes out. And I call the partitions that I get in this summation over all things in between lambda 1 through lambda m minus 1. So there's lots of ways of stitching these pipes together now, right? Because maybe I had a few things coming in. They can kind of get rooted in lots of different configurations and come out. And I sum over all ways of doing that. And I don't restrict myself to what comes out horizontally, of course, assuming it's a 0 or a 1. This is a pictorial representation of that. And you can just check that makes sense, right, from the picture. And similarly with the Q, except I just replace the thing coming with the 1 by the incoming with 0 with incoming with 1. So now I claim that this p lambda is a symmetric function in a1 through am. A priori, not at all obvious, again, for the same reasons as with sure, right? On the other hand, well, maybe we can do something. Now, okay, I'm not going to write it down, but remember there was initially a version of Yang-Baxter that involved just the A-type vertices, right? The A's would swap, and there would be some cost associated. So I'm going to use the L infinity limit of that to prove this symmetry, okay? So what do I do? So first of all, let me write, I don't change the symmetry properties of this if I multiply by a1 through am, right? This is a symmetric product. So I'm going to rewrite this, and I'm going to, well, I've multiplied by something. So what I'm actually going to do is I'm going to augment this with one additional row where I have capital M minus the length of L plus the length of mu arrows coming in here. Now, and I have force 0 arrows coming out here. Now that might seem like a weird thing to do. And it's not immediately obvious why just doing that adds this factor of a's. But the idea is the following. The number of arrows that ultimately need to exit the right side of this picture is the difference between the length of lambda and the length of mu. Right? That's the number of arrows that exit. And so what I'm doing here is I'm putting in exactly m minus that difference. And what that means is that every time an arrow exits, there's kind of enough arrows in here that at every level, regardless of what's happening here, I end up with an arrow coming out. And eventually they exhaust themselves, right? Because I can never, let's see. So each one of these forces an arrow to come out horizontally. Let me think for a moment why. Well, because, right, I choose as my top boundary is 0. And when I do that, you see I have as many, the total number of arrows that's going to be in this column is m. And by conservation, the total number of arrows that come out on this edge needs to be m. And if I fix this to be 0, each one of these needs to be a 1. So when I do that, you see actually the weight of each one of these little pictures becomes equal to a. So this one becomes am. This one becomes am plus 1, or sorry, minus 1, and so on. And so by doing that, I get this factor of a's. Now the reason for doing this is that now I can apply Yang-Baxter. Okay, so how do I apply Yang-Baxter? So what I do, I'm going to use a version of Yang-Baxter that just involves these a's. And what the version is, it basically says that if I take 0, 0 as my entry, and then 0, 0, which has weight 1, and then this sort of infinite A1, A2 picture, that this is equal to the picture where I've pulled it through and now I have a 1, 1 picture. So this is, I can leave it to you to check, but this is the L goes to infinity limit of the original form of Yang-Baxter, not involving these B's. So you see, I have exactly that setup. I have 1s coming out on this side and 0s on this side. And so I just use the Yang-Baxter to keep flipping around each layer. And when I do each flip, I don't change the weight. And so I can flip arbitrarily these A's, and I get the exact same picture. I get the exact same weight partition function. And so that tells me that, in fact, this p lambda vector A times the product of the values in A is the same as p lambda tau for any permutation A times the product of the tau A. So that gives me the symmetry by just using this Yang-Baxter relation. And of course, the Q's symmetry is the same. So a nice exercise is to prove that directly for the Schur case and just see how that works out. Okay, so the last thing I want to do is relate the tell you what the Hall-Littlewood process is and how it relates to stochastic six vertex. And that seems complicated, but let me just draw a picture, and the picture hopefully will make the idea clear from what's written in the notes, and then obviously you can ask questions. So Hall-Littlewood process is going to be defined precisely in the same way as Schur process, except the only difference is that when I have my downright path, depending on whether it was a right path or a left or a down path, I use P's or Q's. So I use the P's on the horizontal and the Q's on the vertical. Right? So as usual, I have my A's and my B's, and so the P's get associated with the A's and the Q's with the B's. So I define a probability measure. I know how to normalize it because I have a skew Cauchy identity. I define a probability measure on sequences of partitions indexed by downright paths by products of these P's and the Q's. Now you see there is a Gibbs property associated to it. I don't write it down because the P's and the Q's were themselves defined in terms of a vertex model, a product of a bunch of terms that somehow factorizes in a very nice way. So there is some generalization of this geometric non-intersecting Gibbs property that holds true for this Hall-Littlewood process. But the remaining question is, who gives a shit about this? How does this relate to the stochastic six vertex model? And so that's the last thing I want to explain to you. So let's write down let me first write down what the so I'm going to consider, I could do this for arbitrary downright path, but let me consider a downright path that kind of goes all the way to the right and then all the way down. And I have my Hall-Littlewood process associated to it. So I'm going to write my Hall-Littlewood process. It's a measure on lambda 1 through lambda m plus n minus 1. I'm going to write it in a picture form again. Okay, so how am I going to write it? Well, I start with an empty partition. I end with an empty partition. So I'm going to draw it in the following way. So I have an empty partition and I have a B1. So I'm actually working kind of this side over. It doesn't matter. And then I go up. I have some number of these B vertices up to B n. And then I have a bunch of A vertices, AM to A1. And then I have an empty partition. And I need that these are zeros, and I need that these are ones, as usual. Okay, maybe I'll draw a 4x4 case. And my measure you can think of as the probability of seeing lambda 1 through lambda n is the weight of putting in that the intermediate, the things that stitch together these different layers are lambda 1 through lambda m plus n minus 1. Okay? So if I want to know the probability under my Hall-Littlewood process of seeing the sequence lambda 1 through lambda m plus n minus 1, I just put these values in and I compute the weight of this picture. And of course, for a given value of the lambdas, I get some collection of outgoing arrows as well. Now, that doesn't quite give me the probability. I need to normalize it by the partition function, right, by the sum over all configurations. And actually, there's a very nice way of doing that, which is to insert in a bunch of crosses. Right? The partition function by this skew-Schur polynomial, by this skew-Cauchy identity, will be a product of a bunch of things of this form. And so you can show that that if I specify boundary values here, of course I need that these are still zeros here, and these are still ones. The product of these crosses, so I associate, the spectral variable follows the line, and so the value, for instance, of the spectral variable here is the product of AM and BN. And then here, this would be the product of A1 and B1, and so on and so forth. So this is just the product of a bunch of terms of the form of 1 minus AI Bj over 1 minus TAI Bj. So this is a deterministic factor here that normalizes the probability measure in the lambdas. So this is the pictorial version of the Hall-Littlewood process on this path. Now, what I'm going to do is I'm going to ask about a particular marginal. So I'm not going to look at the whole process. I'm going to ask, what's the probability that the outgoing arrows here follow some sequence? Say 0, 0, 1, 1. There should be some conservation. Let's see. So I need the number of, so this sum should be 4. So the number of things that come out should be 4. And I guess that this satisfies it. Maybe I put a. So now I'm asking, what's the probability? So this is really giving me a probability measure that I have a 0 coming out, a 0 coming out, a 1, a 1, a 0, 1, a 0, 1. So this is the sum over all potential weights inside of the lambdas that would produce this sequence of really length differences, right? This is the length difference between the partitions that I get, my lambda 1, my lambda 2, my lambda 3, and so on. So this is really a marginal of my process. I'm asking about what's the probability distribution of this particular marginal, the marginal of length differences. Okay. Why? Why do I ask this? Well, here's the idea, and then we'll be done. I'm going to sequentially use the Yang-Baxter equation. So I have some probability of this length sequence. And now I use Yang-Baxter. Yang-Baxter is not going to change the weight of the picture, right? So I'm going to use it starting on the inside out. And so I'm going to kind of think of my B1, my Bn as shifting upwards. I cross it by AM and then AM minus 1 and then all the way up to A. And so when I do that, what I get is a picture. I get a picture where I've moved my Bm up to the top, and I have all my A's, and I have the rest of my B's. And on the right-hand side, I pull out a cross, and that cross kind of gets pulled through a bunch of things. So I end up with a cross with, I guess, 4 things coming out in the end. The outputs here stay the same, so I have my same sequence, 1, 0, 1, 0, 1, and then 1, 0, 0. So do you see what I've done? Now I have Bn minus 1 here. I still have my A1 through AMs. And over here, I've just kind of pulled this cross through. So I have less things to cross. So this, I still have 4 of them. And then I have 3 of these. So the weight of these 2 pictures are the same. I'm going to continue doing that. And this will be the last picture I'll draw. If I continue now, maybe I pull Bn minus 1 up to sit underneath, and then Bn minus 2, and all the way up to B1. What I get is the following picture. So I still have my inputs 0, 0, 0, 0, and my outputs 1, 1, 1, 1. And let me draw this a little smaller. I have my B's up here, and my A's down here. So this is Bn to B1, and then this is A1 to Am. And then over here I actually have a 6-vertex model with 4 incoming and 4 outgoing arrows, and then the same sequence of 1s and 0s around the boundary. But you see, the B's, oh, sorry, the A's, let's see. Let me write this down here. Oh, sorry, I switched the zeros go on top. And when I do Yang-Baxter, I don't change the input. So I have 1s and then 0s. The weight of having all 0s come in, and I have nothing coming in from below, this forces that this is just a completely empty situation. So on the right, I have all 0s, and the partition function here is 1. And likewise here, because nothing is coming from below, these 1s just cross straight through, and I have a partition function 1. And so what I get in the end is a boundary condition, an initial condition for the stochastic 6-vertex model, which is all 0s and all 1s. And then I've specified the outgoing arrow configuration. An arrow comes out here, 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 and here, which is equivalent to specifying the height function. So the height function of the step initial data stochastic 6-vertex model around this sort of downright path, you rotate yourself by 45 degrees, is equal in law to the marginal of this Hall-Littlewood process on the length differences. And that's the theorem. And that's what endows the stochastic 6-vertex model with this relation to Hall-Littlewood processes. And then, of course, the question becomes, how the hell do you study these Hall-Littlewood processes? And like I said, that's a question in its own right that I'm not going to get into. So let me just kind of summarize. We've seen now really 3 mechanisms for relating probabilistic models to these types of measures on partitions. So one is just through the skew Cauchy identity, and you could just try to prove these things directly. One was through this RSK correspondence, these bijections that also kind of produce refinements of the skew Cauchy identity. I didn't go into the details, but RSK allows you to refine versions of these skew Cauchy identities. It allows you to construct these dynamics. And then Yang-Baxter provides yet another refinement of this. In all of these cases, you can use these connections to relate very nice probabilistic models, last passage percolation, the polymer models, stochastic 6-vertex, and various generalizations to measures written in terms of these sort of skew symmetric polynomials. These polynomials have their own tools then associated to them. You can associate them to Gibbsian line ensembles, and you can use that as a technique. You can also, in some cases, associate them to determinantal point processes in the Schur case. In these more complicated settings, you need to use more complicated tools. So you can use what are called difference operators, or you can prove different formulas for these Hall-Littlewood polynomials. You can eventually, with work, consider asymptotics. And this is a field that's been developed really in the last decade for these more general types of systems. But either way, this allows you to ultimately analyze the asymptotic behavior of these models. We saw this worked out in the case of last passage percolation, at least in some degree of detail. And through these algebraic properties, you can then access all sorts of interesting asymptotics that should themselves be universal. And then the next challenge is to prove that these are universal in the same sense of a central limit theorem. Okay, so I'm going to stop here. There's more details in the notes, and I'm happy to answer any questions. Okay, thank you.